Hey everyone, this is um, the final video I'm going to make for chapter 16 of carboxylic acids and esters. This is kind of an addendum to the other ones that I've posted. Again, those ones were made years ago, and the book is a different edition, and they've, I guess, added different things into there that I have in my PowerPoints here, in my slides here. So this one is to basically fill in the gaps if you're looking at the PowerPoints. So the first thing is I never really gave many examples of carboxylic acids. So you can see here on this slide, I have a few examples. The first of which is butanoic acid. This is the chemical responsible for the flavor and smell of butter. Again, butane, its name comes from the fact that the first chemical that was isolated with only 4 carbons was from butter. And it was, in fact, butanoic acid right here. And so that's why it has its name, butanoic. And everything with 4 carbons follows that trend of having but in part of it in its name. And then the second one is benzoic acid. We've used this in lab. You can see it's got a benzene ring and it's a carboxylic acid. The third one on this slide is acetic acid, also known as vinegar. So those are some 3 commonly used carboxylic acids. The slide here has a table of names and sources of some other carboxylic acids. So you see first one on here is formic acid, and that comes from ants. When they're like chewing things up, they make formic acid. It's the simplest carboxylic acid, so I'm going to draw that one right here. Give me a second while I change the color of my pen. But formic acid is going to have this structure. It has 2 hydrogens on the carbonyl. I'm sorry, it does not have 2. It has a hydrogen and the carboxylic acid. I was thinking of formaldehyde for a second. But formic acid has the hydrogen, so it's part aldehyde, and it has the OH bonded to the carbonyl, so it's part carboxylic acid. But carboxylic acids are higher up on the priority list, and so you can see that this is officially a carboxylic acid, not an aldehyde. The other ones on here, they have acetic acid, propionic acid. You can see it comes from Swiss cheese, and its name means first fat, and so in Greek, because cheese has fat in it. Butter, butyric acid. Valeric acid comes from valerian flower plants, the roots of them. Caproic acid, caprylic, capric acids, those come from goat fats. And if we had been doing labs, you would have seen that we would have been using one of these to make the hand lotion in the lipids lab. Next, you have palmitic acid there, which comes from palm oil, and stearic acid, which comes from cow fat. So steer, like it's from a cow, a steer. Even though this is spelled differently, it's from the Greek root, not the English. In English, we spell steer as in cattle or cow, like with 2 E's. The slide here has some more common carboxylic acids, but they're specifically dicarboxylic acids. So you can see right here, the first one is oxalic acid, which has this structure. That's the simplest dicarboxylic acid. It also has the name ethane dioic acid because it only has 2 carbons, 1 and 2, and it's got 2 carboxylic acids. So ethane dioic acid. Oxalic acid comes from a lot of leaves, that like in lettuces, and like specifically spinach is high in oxalic acid. Another one would be rhubarb, which the leaves have so much oxalic acid in them that they are poisonous to us to eat. You may not know what rhubarb is, but to me, a strawberry rhubarb pie is like my favorite. It's acidic, as you might guess, so it makes the pie tart. But you don't use the leaves in that pie. You use the stems only, which kind of look like celery sticks, but they're reddish, greenish, and they're sour, and so it's really good to me, at least. Oxalic acid and or salts of those, like carboxylate salts of these, actually can build up in our bodies, and they'll ultimately lead to kidney stones. So you don't want to have kidney stones, obviously. So you would want to avoid eating the leaves of things that have a lot of oxalic acid. I mean, yes, spinach has a lot, but if you're exclusively eating it, you might want to worry about it, but not many people do that. Other ones on here that are commonly used are malonic acid, succinic acid, glutaric acid, and adipic acid. The malonic acid, its name actually means apple in Greek, and one of the purposes for it, and why it's relevant to put in here, is that it is in complex 2 of the electron transport chain, so it has an important part in the production of ATP, as does the succinic acid, which is in the mitochondria and a part of the electron transport chain. Adipic acid is also relatively important. It's actually the most highly produced dicarboxylic acid on Earth. 2.5 billion kilograms of it are made every year because it's useful in the production of nylon, and obviously lots of people need to have nylon pants, so there's a lot of this stuff that's used. The slide here is just showing ants with some breadcrumb or something like that, and again, the name formic acid comes from the fact that ants produce formic acid as a form of defense mechanism, like they spray it at predators for them, and if you stand over and smell an anthill, it's supposed to smell like something very acidic, and it turns out it's formic acid. It's also used as an antibacterial agent in society from us, so that's an interesting use for it. That who would have known that ants are going to produce something like that? One thing that was missing from the previous videos in the naming of carboxylic acids is the common naming system, where we have the alpha, beta, gamma, delta, and then if this was like one carbon longer, right over here, you'd have the epsilon carbon there, alpha, beta, gamma, delta, epsilon. And so if I ask for the common name of a carboxylic acid, you can see this one here, it has beta hydroxybutyric acid. I've spelled butyric wrong. That's okay. Butyric acid. There you go. Fixed it for you. And then you can see that the carbon right here is the beta carbon, because it's always the first carbon. You start the naming of these, or the labeling of the positions, after the carbonyl. So this is the alpha carbon, and then this is the beta. So beta hydroxybutyric acid, and then over here we have the alpha position as well. And so this would be alpha hydroxy. I actually have, again, the name wrong here, because if you look at it, there's 1, 2, 3, and 4 carbons. So its actual name is alpha hydroxybutyric acid. And obviously I need to update my PowerPoints again, because I missed that all these times. This slide here has some common carboxylic acids on benzene rings. So you can see the first one here is called metatoluic acid, but really its like official name would be 3-methyl benzoic acid, because if we're doing the IUPAC names, because the carboxylic acid is highest up in the priority list, so that automatically is carbon 1. There's 2 and 3, and you have a methyl group right there, so 3-methyl benzoic acid, or metatoluic acid. The second one in the middle here has the name orthobromobenzoic acid, but this would actually be named an IUPAC 2 bromobenzoic acid. And then the final one on the right is called phthalic acid in its common name. It's way easier if you could memorize that. Not that I would ask you to do that in a test, but its official name is 1,2-benzene dioic acid. Dioic acid, which is a lot. But you can see the 2 carboxylic acids are at carbons 1 and 2. If you look at Wikipedia, it lists the preferred IUPAC name as benzene 1,2-dicarboxylic acid, which also is a lot. I don't really like calling it dicarboxylic acid. Dioic acids are, to me, preferred. But either way, just kind of finishing it up, you can see the M and the O here. Those represent meta and ortho, respectively. Meta just refers to the fact that the methyl group right here is 2 carbons away from the carboxylic acid. Ortho says that the bromine is and the carbon adjacent to the carboxylic acid. So ortho and meta, those are old naming systems. They're no longer technically official, but they used to be up until it was actually 15 years ago or so. Another slide with common carboxylic acids. You've got benzoic acid, salicylic acid. That one we're going to use or have already used in lab. That's wart remover. And then acetyl salicylic acid is aspirin under its trade name. And so you can see here's the acetyl group right here. And then if you look at, I'm going to re-highlight things in yellow here. The salicylic acid has the benzene ring, as does the acetyl salicylic acid. It has a CO2H, which this has, so they've been flipped there. Salicylic acid has this oxygen, and so does acetyl salicylic acid. And so in red, I'll put right there, the hydrogen has been replaced with the acetyl group, so hence its name, acetyl salicylic acid. Something missing from the slides as far as reactions was the preparation of carboxylic acids. Technically, we've already seen it in earlier chapters with the alcohols and the aldehydes and ketones. The alcohol, if it's a primary alcohol, it can be oxidized into an aldehyde, and aldehydes can be further oxidized into carboxylic acids. So we have technically seen this already, but that would be it. And then if you had a secondary alcohol, like something like this, and you oxidized it, that would go onto a ketone, and ketones cannot be oxidized. So the only way here that we show to make carboxylic acids is by, you might have to start with a primary alcohol, but the intermediate part is the aldehyde. You have to have an aldehyde to get to the carboxylic acid by oxidizing it. There was a part missing for naming salts of carboxylic acids, or the carboxylate salts, and so it's really pretty straightforward. But you see here it says the salts share their names with the parent carboxylic acid, but the "ic" suffix is replaced by "ate." So, for example, if we had this ethanoic acid and we stripped off the hydrogen with some base, then this would make this carboxylate salt and water, and the name of this would be ethanoate right there. Now, if we were to add to this and say, well, it's not just a hydroxide, you have to have a cation with that, and we're going to use sodium hydroxide. The sodium ion would be attracted to the ethanoate ion, and so the name of the whole thing would technically be sodium ethanoate. As you can see in Rule 2 there, the carboxylate name is preceded by the appropriate cation. As far as properties that were missing from the other videos, boiling points was mysteriously missing, and so I've discussed ad nauseum all of these types of compounds, why they have higher boiling points and higher solubilities than alkanes, alkenes, alkynes, etc. You can see the carboxylic acid has a lot of polar portions to it, and so these should be very soluble with each other, or not with each other, but they should be very soluble in water, as mentioned earlier. But they're also going to have very high boiling points. A lot of carboxylic acids, or I don't want to say a lot, but there are many examples of carboxylic acids that aren't even solids at room temperature. Benzoic acid being one of them. And because you have so many polar spots in them, and you have a hydrogen right here that can hydrogen bond, they're going to stick to each other very, very well, more than alcohols. And so they have much higher boiling points than alcohols, which have much higher boiling points than alkanes and alkenes and alkynes. So you can see in the slide here, there's this trend in boiling point, and it's increasing for these compounds going to the right. You can see the molar masses of the three of these compounds, the aldehyde, the alcohol, and the carboxylic acid, are very similar, but the boiling points increase. Just the carboxylic acid has an alcohol, essentially. We don't call it that, as does this 1-propanol, but it also has the partial negative oxygen there and that partial positive carbon. So it's more polar than alcohol, and therefore it's going to have a higher boiling point. And at the bottom, you can see that the carboxylic acids can actually hydrogen bond with each other 2 times, whereas an alcohol would only be able to do it once. Like, there's 2 positions of it on each carboxylic acid, whereas the alcohol only has 1. So you could have the lone pair on that oxygen going to just the 1, and so it's just not going to do it as much. The table here shows the boiling points, solubility, and acidity of several carboxylic acids, based on size, and the last one there, structure. So you can see going down this first column on the right, the boiling point increases because they're just getting heavier. And the solubility, as usual, is going down the more carbons you have in the chain, but you can see that hexanoic acid is slightly soluble in water, whereas most of the other ones, for the alcohols, aldehydes, ketones, those ones became insoluble between usually 4 or 5. And then benzoic, it says, is slightly soluble. Now, the other interesting thing is to look at the acidity of the carboxylic acids here. So you have 1.8, 1.8, but it's 10 to the 4th and 10 to the negative 5th. And so that means the acidity is dropping, or at least it dropped significantly between methanoic and ethanoic acids, and then between all of the rest of these it stays pretty stable, 1.3, 1.5, 1.5, 1.4, they're pretty similar to each other. And then benzoic acid is actually surprisingly higher than the rest, and it just has to do with the fact that benzene has, let me draw here for you, has the ability to donate electrons through resonance. So let me get this in here. So what's actually going on is if we have a base attack this carboxylic acid, it's going to take off that hydrogen right there and leave a carboxylate salt. And so let me just erase this and show that. So you're going to have now 3 lone pairs and a negative. What I'm going to also do is pretend that these electrons are going to shoot up to the oxygen, which what that's going to do is break apart the double bond here. Actually, just do that, creating a single bond and 3 lone pairs on this oxygen, giving that a negative. But now this carbon is going to have a positive. And so what you'll see is that that positive charge is close to that double bond because they're actually conjugated. And so what can happen here through resonance is that that positive charge can spread around the whole ring. And so let me show that. So we can delete that. Let me get a smaller one here. We can delete all of this and that. All right, that's going to give us a positive charge here and a double bond there. Right, since I had the arrow in yellow, let me fix that to be yellow. And then this double bond can donate to there, resulting in the positive charge being moved around over here, like that, and so on and so forth. So essentially what we get are partial positive charges all around it, all around this benzene ring. You have a partial positive here, partial positive there, partial positive up here, partial positive right there. So through resonance, that partial positive right there is actually stabilized, whereas in acetic acid, or the acetate ion, it's not stabilized. If I draw that in, there's a partial positive there, but there's nothing to donate to it, so it can actually be less stable as the carboxylate salt right there than what you would get for benzoic acid.